Hello, I'm Mike McCulloch. Today I'm going to talk to you again about time, and I'm going to use two thought experiments which have been widely discussed to show you why time may not be exactly what we thought, how it may differ, and exactly how it differs. Okay, so the first of these thought experiments is the Einstein-Podolski-Rosen experiment, published by those guys back in 1935, I think it was. So that in this experiment, there are two spin zero particles which spread out from a common origin. They're entangled, they spread out, and when they're very far apart, you measure the spin of one of these particles and it happens to be up. So by logic, you then have to conclude that the other one is down. But the problem is that in quantum mechanics, there's nothing in the wave function that prescribes the spin. So you have to assume either that you have to add some hidden variable to quantum mechanics to code for the spin, and this was Einstein's suggestion, or you have to allow that relativity is wrong and information can travel faster than the speed of light. So those are the two options, but there is another one, and that is quite appealing to me because, and it always was, because time is not very well understood in physics. It's not well treated. So can we modify time to account for this? There's also the other experiment is the Young's two-slit experiment, where a laser is fired at two slits. Now, normally the photons go through both slits, according to quantum mechanics, interfere with each other, and then you get an interference pattern on the other side of the two slits, which has been seen quite readily. But if you happen to measure which slit the photon goes through, then the interference pattern disappears because you're forcing the quantum system to decide. The interesting thing is that another test has been done, a variant of this, where they decided whether to measure which slit the photon went through after the photon had gone through the slit, and it still had the same effect, which means that the measurement was somehow having an effect backwards in time, which again alludes to our lack of understanding of time. Okay, so I published a paper in 2021 after many decades of thinking, actually, and I was helped at the final stage by Jaume Gine from Spain, who helped me formalize the paper and get it through peer reviewers. And the idea is this: that you define time in terms of something that can be measured. So, as so often in my work, I've started off with the uncertainty principle, Heisenberg uncertainty principle, the energy time one, which is shown here. So the uncertainty in energy times the uncertainty in time is got to be greater than or equal to h bar over 2, which is just a very small number, a constant. So that means whenever the uncertainty in time goes up, the uncertainty in energy has to go down. They're complementary in this way. In this formula, you can replace the uncertainty in energy with K times temperature. Well, energy is Boltzmann's constant times the temperature. So what temperature should we use? Well, why not the unknown temperature? So I tried this. So that means that the uncertainty in energy is given by h bar a over 2 pi c, because the k's cancel out. And then if you rearrange this for the uncertainty in time, you get delta t is equal to pi c over a, where a is the acceleration of the system, or particles within the system. So this is nice because it defines time, which is something that it's very hard to, well, I can't say hard to measure because you can measure it, but it's hard to be sure what you're actually measuring because we tend to measure change rather than time. So this redefines time in terms of the acceleration of the objects in the system A, which can be observed quite easily. this also means that if there's no acceleration in a system, which is true for a quantum system, because it doesn't interact with anything until it does, then the uncertainty in time expands or dilates. So would this be enough to explain EPR and Young's two-slit experiment? Well, to cut a long story short, yes it is. So you can put in here for A, v squared over d, where v is the speed of this particles in the system, and d is the length they've travelled. And if you do that, you get that the uncertainty in time is pi c d over v squared. And then if you change, if you say that d over c is simply the time it takes the system to go from the beginning to the end of the process, then you can replace the d over v squared with tau. So you get delta t is pi tau c squared over v squared. Okay, so the great thing about this is that because v is always smaller than c, the uncertainty in time is always going to be greater by a factor of pi, greater than the actual duration of the system. So this means that in the EPR thought experiment, the time the particles take a certain amount of time, might be millions of years, to go from the central point out to the edge where they're measured. But this formula ensures that their uncertainty in time, which means their knowledge, their now, if you like, is much greater than this time. So when they first set out, they already knew what the outcome would be. But we, looking in from the side, we have huge accelerations, so our uncertainty in time is much lower. So we don't know the future, but they do. This also works for the two-slit delayed choice experiment as well, because it shows that when the photons start from the laser heading towards the two slits, they already know the outcome, whether they will be measured by the detector at the slit or not. So they know whether to interfere or not. They know the future. So this is nice. I mean, time has, in my opinion, not been well treated in physics at all, but this corrects it, makes it more measurable, makes it dependent upon the acceleration of the system in this way, and it explains these two interesting paradoxes, the EPR paradox and the Young's two-slit experiment. So yeah, so I hope you've enjoyed this short. Please do follow me on Patreon. It means a lot, and thanks to those who do. And I look forward to making another one of these for you tomorrow. Goodbye.